Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. This morning, the talk from our candidate, Yongfeng Gu, is about reconfigurable computing, which is an area that has had interest recently. And Yongfeng will be telling us what it means to actually take real application and make them run on these machines. Yongfeng is going to indeed graduate, definitely, this summer from Boston University. Here's the talk.
Okay, thank you everyone, and thank you for coming, and thank you for watching my talk today. And today I'm going to talk about accelerating high-performance computing with reconfigurable logic, mostly FPGAs. The motivation of this talk, first, high-performance computing always requires more computation power, but nowadays we are approaching the power density war, and this is a very famous figure from an old Intel slide, and we are approaching somewhere here if we follow the prediction. Fortunately, we didn't go to the situation there because we have multi-core these days. But the problem is, even with multi-core, it's still hard to map high-performance computing application to multi-core efficiently and still keep linear scaling. And this is just a conversation to complain about how hard it is to map the problem to multi-core. So we are thinking something else, some alternative architecture. And in this talk, I'm talking about configurable logics, FPGA. And we are thinking FPGA is promising for this area because FPGAs, they are commodity parts. We can get them from market with a reasonable price. And also FPGA is kind of well balanced among performance, generalization, and the development effort. But as we will see in the rest of the talk, we still need a very careful design. Otherwise, we will not achieve speedup. First thing first, what is FPGA? And the FPGA stands for Field Programmable Gate Array. One sentence for that, FPGA is a class of circuit which contains programmable logic components and programmable interconnections. With these programmable components, we can implement different logic functions, and with connections, we can combine these components to implement an even big logic function. And it has two phases. Before configuration, FPGA is kind of general purpose. It can be implemented for various applications. But once it's configured, it becomes application specific. We put most of the resources just for the task we wanted it to do. Some traditional applications about FPGA include glue logic on PCB board. We are combining our signals, doing onboard registers. People are using them for prototyping circuits to have a real chip and can do the validation. And for some simple application and a small requirement, people just do using FPGA as ASIC and plug them on the board. And why are we thinking about FPGA for high-performance computing now? And there are many technologies that help us. And the first one, as we can see here, the semiconductor technology. Now FPGA are using advanced as a 65 nanometer technology, and there are tens of million gates on the chip. And with these transistors, we can implement a lot of processing elements. For some application, the number can even be 1,000. And also because of the FPGA architecture, these processing elements, they are working in parallel. And also we can implement them in very deep pipelines, so the parallelism is even huge. Another one is because of the configurable connection. The interface, memory interface, the I/O interface can be very flexible, and the on-chip and off-chip bandwidth can be easily reached 1 terabits per second. And the system-on-chip technology offers many dedicated hardware components, such as SRAM, embedded DSP modules. These parts are not configurable, but they are of very good performance, and for some application, as we will see, they are very important. And as a result, there are many supercomputers, such as SGI, Cray, SRC. They are using FPGA as a general-purpose, reconfigurable coprocessor along with the traditional microprocessor. To map FPGA with the high-performance compute problem is still challenging, and here are some challenges we listed. The first one we listed here is MDES law, because we only want to spend our resources, our effort onto the hotspot of the problem. But the potential speedup is limited by the part of the problem we are accelerating. So we have to be very careful about the problem partition. And the second challenge is about the operating frequency. So most FPGA chips are running slower than microprocessor by a factor of 10. And the most advanced chip nowadays can run as fast as 500 megahertz, but it's still slow. And the third one, we got speed up because we explored the parallelism. But on the overhead of the parallelism in the problem, there are serial parts, there are communication, synchronization overhead. And these overhead prevent us from scaling the performance linear with the processing element we can allocate. So this part also needs very careful design. And the fourth one is the sharp learning curve. There are many application experts. They are good at programming. They are good at even parallel program. But developing FPGA or developing reconfigurable circuits need different skills, experience. And these things is kind of hard for one people to handle both of them at the same time. So a short conclusion here is high-performance computing can use FPGA, and there are very good potential speed up. But we need very seriously careful design, either in the problem itself. Also, we may need to have some tool to help us to achieve the speed up. And here are some applications I've been working on in my recent years. And first one is molecular dynamics, and I will talk more about this later. And the next one is rigid protein docking. It's kind of a three-dimensional pattern recognition. And another one is approximate sequence matching. We are doing matching between DNA sequences and the protein sequences. It's more like a BLAST-like algorithm. And some applications, so many of you are expert at these areas, such as computer vision, image processing.
This Cray was the Cray XD. Has anybody with the NSA purchased it? The Cray machine was a FPGA.
They have FPGA as a coprocessor.
Sorry?
They have an FPGA as a coprocessor.
Yeah, but has anybody except the NSA purchased it?
Well,
I don't think so.
I don't know.
So they probably do it for sequence matching.
They don't talk.
Actually, I have seen many publications about the SRC machine, and I think the company support a lot. And SGI has some publication, but XDI, well.
I can't hear you.
And Lawrence Livermore, they use it, but I think they use
The
it
XD
remotely.
machine?
Yes.
Oh, interesting. But they're not into crypto.
Okay, let's go through this application quick. So on cryptography, data compressing, search engine image, information retrieving, machine learning, pattern recognition, and more and more and more. So in this talk, I will particularly talking about molecular dynamics, and actually there is not enough time for talking about the whole thing, and I will pick a piece of my work. And the recent work is about multi-grid method for the long-range force computation. And then I will give the description about FPGA design, implementation, and the real-time discussions. So why we are thinking about molecular dynamics and what does it do? Molecular dynamics, which is the core of the computation chemistry and computational biology. Researchers use the molecular dynamics to study many applications such as drug design, to understanding the disease process and to understanding the behavior of proteins. And for some scenario, it's hard to observe some phenomena, so people have to do the simulation. Or for drug design, there are a lot of candidates, and it's hard to try one by one with wet lab, so they can filter this with molecular dynamics. And here is an application published in 2004 about protein aggregation and protein folding. And why we want to accelerate molecular dynamics? Because molecular dynamics runs always very slow. And nowadays, even we want to simulate some side chain action, the simulation skill usually involve mega or less than mega particles for mega or something around that time steps. It takes even weeks and months to finish on a kind of powerful machine. And if we want to go this side, either these days we have to use very simplified force model and the computation model, or we just cannot do that. And this topic, as we can see here, it's kind of hard in these days doing FPGA acceleration for molecular dynamics. And the people are doing this project in different directions in the design space. The scope of MD acceleration, so how to partition the problem, and the precision, and the arithmetic mode, such as the first one, and this one, and this one. They are doing double precision. And the second one, they are doing fixed point on computation, and we are doing something in between. And the basics from MD code, target hardware, and design flow. So, and one thing to mention here is most of the work here, they are only accelerate on the short range force. Of course, this is the hardest part. But once it has been accelerated, the long range force becomes more significant. And we have, as I know, we have published the first publication about accelerating long range force. So I think that will be more interesting, and I will talk that one. Before goes into the multi-grid, let's see what does molecular dynamics work. Basically, it is a two-phases application, and two phases: motion force application and motion update. For the force update, given the particle positions and their types, we can calculate the interaction between particles. And based on the interaction, we can calculate the acceleration on each particle. Then we assume in the next short period of time, the acceleration will remain constant. With their old position and velocity, we can update to get their new velocity and new positions. That's the motion update. Since the force computation is taking care of the pairwise computation, so it's kind of O(n) squared, but motion update just goes through every particle, just O(n). So we think looking more into the force update. And here is a typical force field. The first 1, 2, 3, 4 items, they are related to bond, either covalent bond or hydrogen bond. So they are still of O(n) complexity. And the non-bounded forces exist between any two particle pair, so it's O(n) squared. And that is the part we are going to accept with FPGA. And this part usually takes more than 80% of the computation effort. Here are two typical non-bounded forces. One is Lennard-Jones. This is the equation, and this is the Coulomb force. Okay, let's see Lennard-Jones. The Lennard-Jones force has a very good feature. It decays to zero very fast. So we can apply a cutoff here, and we just take computing whatever two particles are within this distance, and we don't care about those are far away from each other. But for the Coulomb force, it decays to zero, but it's not that fast, and we can see later. If we using the same techniques here, we will have some trouble about error. So let's see what to do. Let's just let me quick get through how to do the Lennard-Jones. Since we're only caring about the particle in very close neighborhood, we can cut the space into small pieces. It's called a cell list. And we only care about the neighboring cell because these cells containing the particle we are going to calculate. And those final way, we just don't want to spend any time on it. So the time scales reduced from ON squared to ON. And here are many variations about how to implement the cell list. But how about the current force? If we cut it off, and so it becomes ON as the Lena-Jones, but the error in some application is not tolerable. And there are many clever methods to accelerate the long-range force computation, and as famous as this one, EWOS, and the next two are variation about EWOS, and the computation complexity reduced to n log n. And there are groups doing FPGA acceleration about the EWOS and its variation methods, but there is no full implementation has been published. The difficulty is quite obvious because these methods deeply rely on three-dimensional FFT, which is very, very hard for FPGA. So we are thinking something different, and that is good for FPGA, which is multigrid. Okay, let's see what multigrid is. First, we just go through the current force computation in general. The general problem is two steps. First, we calculate the potential from the potential distribution from the charge distribution. And then we can get the force on each particle based on the field from the potential distribution. And the hard part here is obvious because we want to transfer the charge distribution to force distribution. The naive way is always resulting in an all-true operation, so it's ON squared. That's the problem. And one improvement we can do, obviously, we can apply grids. See, we apply the charge in the continuous space to the grid space, and then do the computation, the transformation from charge distribution to potential distribution on the grid space. It's easier. And then we apply the potential from the grid space to the charge position and to the force computation. So this is the new method we want to do. And here are the steps, the verbal version of them. Applying charge from continuous space to the 3D grid, and apply the potential from 3D grid to the continuous space. And here we are solving the Poisson equation on the grid instead of in the continuous space. And we are thinking using FPGA to do that because FPGA is really good at these three steps. For example, if we want to do to assigning a charge onto the grid, we have to access the grid point for a couple times, and then we do the computation and for a couple clock cycles. That's the traditional software style. And for hardware style, well, we can access the memory simultaneously, get all this data, and do the computation with some pipeline. So we can generate the result at every clock cycle instead of multiple access and multiple cycle computation. And on the grid, we are doing computation on the grid, so it's convolution basically. And in the serial processor, we are doing 3D FFT if the convolution size is big. But on hardware, we can do something else. Or with FPGA, we can generate processing element and replicate the processing element and combine the processing elements, stack them together and combine and build it into a historical array, which has a very good bandwidth, throughput, and generates the result every cycle. So that is good, what FPGA is good at, and that is what the grid computation needs. There's still one problem we left here. As we see, the interaction between continuous space to grid, that's easy. But bad news is naively we translate charge distribution to potential distribution. It's hard because if we want to maintain accuracy, the density, the number of grid points should be equivalent to the particle number, and that still goes to ON squared. So we need something to accelerate this computation. That is multigrid. And I think many of you are expert about multi-grid because this has many applications like image processing, numerical computing. The basic idea is computation on the grid can be easier than in the continuous space. And then with the multi-resolution idea, we can calculate the short-range part, which is also the high-frequency part on the final grid with a small neighboring area. And we calculate the long-range part or the low-frequency part on the coarser grid. So we can involve more information from farther grid later, and go on and go on. And the final, we can solve the problem because we reach the finest, the coarsest grid. There are limited number of variables, so we can solve the problem directly there. And this comes into what we call a V cycle. It just when we go down in this direction, the number of grid points just reduces, and when we apply the result back, so the number of grid points increases. So that is called the V cycle. And this is a general steps for multi-grid and many applications. I'm just showing here one of them, like image processing. Okay, let's see how can we map Coulombic force computation to multi-grid method. First, this is the code we just saw, how to use cutoff. And we want to map it to multi-grid first. We cut this curve, we split this curve into two pieces with a smoothing function. And then the first part of this becomes a high-frequency part and it can be cut off. It's a short range, so it can be cut off. And then the rest of them becomes flatter. And we only compute this part with multi-grid. And this is the idea. One LoRa is split into two parts, and this one is the short-range part. This is the long-range part. GAR here is called smoothing function. And the A here means this part can be cut off at distance of A. So the short range can be computed as on the linear Jones I just taught. And the GAR is the long-range part will be sent to the multi-grid. And here, once we are on the grid, we apply the same idea recursively. So GAR is split into two pieces with another smoothing function called G2AR. And this is the short range part, and it can be computed efficiently on the fine grid. And this part will be computed on the coarser grid. And go on and go on. And once we reach the coarser grid, so the number of grid points is small enough, we can do the computation directly, and then we go back. Now here is a visual version of this. Cut the original force into two parts. This is the short range part with CList. And we assign the particle on the continuous space onto the grid, just the long range part. And we calculate on the high frequency part, we call it correction. And we assign the flatter curve on the coarser grid and do the same thing again and go on. Until we reach some small number of grid points, we can do the direct computation. We translated the charge into potential distribution. And then we go back, because this is the low frequency part, and we incorporate the high frequency part, go back. And finally, we apply the potential on the finest grid to the original particle positions. And this is the flow chart of the previous process, and this is a serial version of the recursive function call. And we can see there are 1, 2, 3, 4, 5, 6 steps. The first and the last steps, they are dealing with the interaction between particle and the grid points. And the rest of them are based on the grid, just doing convolution. AG is interpolation, to assigning the charge from the fine grid to the coarser grid, and the integration grid doing interpolation. So interpret the grid and the potential from the coarse grid to fine grid. And these are the two types of applications. And this one is one input, and then the output is just many points on the grid, or we can do the back way. And the grid correct convolution, just convolution. let's see how well FPGA can deal with this problem. The grid particle and particle computation is just the problem I just mentioned, given the particle coordinates. And we want to assign the charge onto the neighboring grid points. Or on the other side, once we got the potential on the grid points, we want to apply them to the original particle position. But we also need the weight. How can we apply these potentials? And we implement this with FPGA in 2 steps. And one, actually, this one is offline. It has nothing to do with FPGA. We scale the coordinates so that we don't have to divide the coordinates to the division to find out this neighborhood. We just look into the bit string. So we scale it to be a factor of 2. And then we split the coordinates in the bit string into 2 parts. The more significant part indicates where are the neighboring grids. And the offset, we are using this one as an input to the basis function. I'm going to talk later to calculate the weight applying on these neighboring grid points. So that's the second step. This is an 1D example. So GI telling us where are the neighboring points are, and OI is the offset. And this is a third-order basis function from the skill paper. And they have proved the multi-grid method is accurate for molecular dynamics simulation. And we convert this basis function into 2 expressions according to 2 neighboring grid points, and calculated them in this circuit. And the phi 0, phi 1, they are corresponding to the weight, and the d phi we are using for the force interpolation. And this is the circuit we are doing this. And once we get the weight, we apply them on the charger on the chargers. And the input of this tree structure for the charge assignment is the point charge. And then it goes through the 3 levels according to the 3 dimension. And each level, the weights on each dimension calculated on the previous page will be sent to this bubble. And once, one notice here, the bubble of the same color of the same level share the same input, the same weight input. Another input just shown here is just the charge assigned from previous stage. So the calculation takes 1 input, and then it generates p to the 3 outputs, and p is the order of the basis function. But the problem here is 1 input, that many outputs, and how to deal with efficiently. It's a hard problem for serial processor, but for FPGA, we come up with this one. It's called interleaved memory, and we only use that for the finest grid. Okay, so let's see what's the requirement for the memory. There are 2 basic requirements. One is the bandwidth. So we have, for example, 64 data in 1 cycle, so the bandwidth is huge. Another one is we know the data is stored in 1 dimension in the memory, but even in this 2-dimensional case, we want a neighborhood. So how can we get this neighborhood efficiently in a 1-dimensional memory? And the solution for FPGA is we have on-chip SRAM separated. Each one has its own index logic. So we have the bandwidth and we have the index logic to go into the memory to fetch that many data we want. Also, we have the configurable connections and the logic components. We can organize this data into the predefined order. An integrated solution is first published by my former colleague Van Cott in last year. And this is an example of how we implement the interleaved memory. First, for this example, this is a 2-dimensional example, and we want a 4x4 neighborhood. So we use a 4x4 memory bank. So there are 16 banks. And we cut the space into small blocks, and each small block mapping to these memory banks. And 1110 according to 1110 here. And anytime we access given a reference address and its neighborhood, just cover the data from each of these banks. And the problem here is, given a reference address here, we got this data, but this data is not in the right organization we've predefined. We want something like this. And we know the index into each bank, and we fetch them, but the connection of this memory just gives us something like this because of the hard connection of the memory. And we want to reorganize it into this form. We did two-dimensional rotation. This is 1. This is 2. And 2 is because of these two-dimensional cases. So we got this. And it's straightforward. But the idea here is to do this rotation takes logics. And it still takes some time. And it will combine into the memory access latency. And that will be very hard for some application with kind of random access. If you want to do that, probably you will get some read after write hazard. And that will slow down the performance by a factor of 2 or 4. But on FPGA, we do all this combination logic. And we can combine this delay into the memory access latency. So the latency will become small, and the performance of this memory is kind of reasonable for our application. The second kind of types of operation we are doing for multi-grid is convolution. And we use systolic array convolver. And this is very typical for hardware design. And we can see here we have processing element. We line them to get a one-dimensional convolver and stack them together with FIFO. We have a two-dimensional convolver. Then we go to the third order. Yes?
Sorry, 2 slides ago you said that you have to do FFT and it's a problem. Now you're doing convolution, which is much more expensive.
Yes.
Or looks to me much more expensive. So haven't you run out of the frying pan into the fire?
Okay. The idea is we are doing this problem very close to the application. So the application is molecular dynamics for the biology. And with this problem, and this number seems to be can be handled by the direct computation on FPGA. But still, it's hard for the microprocessor. But for FPGA, we have the parallelism here. We can do that directly. So this is one reason. And as we can see here, for this problem, it's kind of easy because we can do FFT. But for some convolution, we cannot do FFT. If the because convolution is basically multiplication and accumulation. But the multiplication, if it's not based on the real number, it's just a general vector computation. We cannot do FFT on that. So this is not motivation for the systolic array convolver. And let's see. Yes, we have limitations. And I'm going to talk about the limitations here. And the convolution involves 2 matrices. And the size of 2 matrices is limited by 2 factors. The first one is limited by the number of processing elements we can have on chip. And the second one is, okay, the operating mode is we initialize the processing element with 1 matrix. And then we stream in the second matrix 1 element at every cycle. And this element is broadcasting all this processing element to do the multiplication and accumulation. So we can generate a result every cycle. So we need to fit 1 matrix into the array, and also we have to fit another one into the memory. That one to the memory is okay because memory is kind of big, but the number of processing elements is limited on FPGA, and that causes us problem to do the convolution directly. And here is a typical setting for the multi-grid method for Chrome force computation. We use 2 level of grids, and the final grid is 28 by 28 by 28, and the coarser one is 17 by 17 by 17. the correction needs a convolution like 13 by 13 by 13. We didn't go further to the third level because the next level, the size of the grid will be smaller than the convolution called here, so we will not save extra computation effort. But even for this, we need a convolution between a 28 by 28 matrix with a 13 by 13 by 13 matrix. But what we have on the FPGA, nowadays my chip can only fit a 4 by 4 by 4 convolution core, so there are 64 elements. But we cannot fit all the 13 by 13 onto the circuit. The solution is straightforward. We just cut the matrix into small pieces and do convolution with B one by one and combine the results. So then in that case, we can handle any big size the computation, so long as the memory can hold the data. And we slow down. Of course, we slow down since we have to cut it into small pieces. But since that's the maximum number of parallelism I can achieve on the chip, so that's the best thing I can do. Okay, next I'm talking about the implementation. A couple slides. This is the platform we are using. This is a Nepalese microsystem FPGA board, which has two FPGA Vertex 2 Pro 70 FPGAs, and we run both of them at 75 megahertz. And this board is plugged into a Dell PC workstation having a 2.8 gigahertz CPU. And we just do the short range and the long range force computation on both FPGAs. So we do the two parts on both FPGAs. And the rest of, such as the bounded force and the motion update, we're still doing them on the microprocessor. And the software doing that is Protomo 2.03. This is the software developed at University of Notre Dame University. And the design flow, we are using VHDL to do the FPGA design, Simplicity Pro for the compiling, Xilinx tools to do the mapping and paste and routing, and ModelSim for the debugging. And the specification of this one, now by using the on-chip, on-board SRAM, we can hold more than 200,000 particles of 22 atom types. And we have two chips, one doing the short range of force, it can do on cell list. And we use another chip to do the multi-grid. And we are doing 35 bits precision semi-floating point. This is different from floating point and fixed number. We are doing something compromising between them. So the number, the format of the number is not encoded into the bit string. And but the binary number or the binary point or the decimal point can vary among several positions, predefined positions. And we use that during the computation, and I will show the results. Yes?
Semi-floating I haven't heard. It's not the same as block floating, so the choice of assumed main binary point is limited instead of being all possible values, or what makes it semi-floating?
Okay, yes, because this name is invented by me, so that's not surprising you haven't heard about it. And I can either talk now or later. I can show some slides in another file about some semi-floating point. And basically, you are right. It's more like a block floating, but the block size is not predefined. And the data is encoded in different stages of the pipeline, and they can be interpreted in different ways based on the stages and based on the data itself. So I can show you some slides later. So let's go through this talk first. And this is the two chips on the board, software running on host, talking with on the PCI bus, downloading data in double precision, and we translate them into the semi-floating on fly. And once we got the acceleration, we send back and do the translation again. And this is the board to FPGAs. And this is the system architecture of the multi-grid coprocessor. And here are a bunch of memories. And this one and this one, I interleave the memory for the finest grid. And the rest of grid are just very simple dual-port memory because they don't need that much bandwidth. And this is the particle grid converter, the tree structure. And this is the cyclical rate grid convolver. Now I'm talking some results we have. Okay. So what do other people do? So most of the multi-grid codes are doing double precision because, well, we thought because they want high and they want accuracy, and also they have double precision unit in their multiprocessor. But we are doing something else, so we need to measure if our method is good enough. So here are two measurements. First is the physical invariant energy. So the energy fluctuation should be as small as possible. And the second one is since we are doing multi-grid, we use the direct computation, which is O(n)² we want to avoid. We use that as the test bench as the most accurate one. And we compare our results with the direct computation. And we call that is the error. So we measure the average force error and the potential energy error. And these methods are also used by computational chemists. They are developing new computational algorithms and to evaluate whether their algorithm is good enough. And for the hardware validation, we use two versions of a tracker code. First, the tracker code mimic the hardware, but they do it does the computation with double precision. And this, under the same simulation setting, it should generate the same results as original software code. And the second version of tracker code replaces the double precision with the semi-floating operations. And it has the exact behavior, bitwise behavior as our hardware, FPGA hardware. But there is a gap between them, so that's why we need to use the physical significance to evaluate our work. This is the simulation we are running for running for the accuracy validation. The model is of 14,000 particles of bovine pancreatic trypsin inhibitor molecules and water molecules. We run this model for 10,000 time steps with original software code and with our FPGA acceleration code version. And we measured the energy fluctuation and both yields. Yes?
If I understand correctly, are you saying that 53 is enough, that you never get overflow in this problem?
Not yet, because 53 is the double precision, so right. It's not getting overflow.
So it is enough?
So the range is enough, but whether it's accurate enough, most of the users, they agree on that. So they publish paper, they do experiments, design drag on that, so I believe that's enough.
Okay.
And so the both version yields similar energy fluctuation here. And let's see on the error. We compare our numeric result with the double precision direct computation. And we have, so this direction is the number, is the space, the grid spacing. So it's 2 angstrom, 3 angstrom, 4 angstrom, 5. That's the grid size of the finest grid. And this is the potential error. This is the force error. And we can see these curves, these lines are the results from the double precision implementation with multi-grid. And these dots are our semi-floating point implementation. They are very close to each other, and actually the difference between our implementation and the double precision implementation is 10 to the minus 4 of the error itself. And since the double precision multi-grid is proved to be accurate by the chemists, and our method is just that many different from them, so semi-floating point in this application is quite successful. And here is some timing data. We did profiling about these 6 operations. In the original software, the grid particle computation takes about 20% of time. And since we have the tree structure and the memory, interleave the memory, and the speed, the efficiency here, we got just reduced to less than 5%. But anyway, most of the computation are doing convolution. And that's why we spend most of the resources on this part. And to generate the time performance, we use a model which has 77,000 particles, and we just run 1,000 steps to generate the speed up. And as I said, I computed the short range force on another FPGA, and that one has 7.3 times speed up over the original Protimo. And our multi-grid implementation has 3.1 times speed up than Protimo. So the overall, because we have some overlapping, so the overall speed up is 7.1. And we also compare with our multi-grid method with NAMD. NAMD is more famous than Protimo and widely used by biologists. And this one is also in the CPU 2006 floating point test bench. But they don't have a multi-grid. They use multi-dimensional PME particle mesh evolution. But they use this method to do the same computation, the long-range uncoulombic force computation. And the speed up, our FPGA version over them is 2.4. And the overall speed up is 6.3. And in some cases, they thought because the long-range force very slow, much slower than on the boundary force, so they only evaluate the long-range force, the PME, every 4 cycles. So based on that, so the speed up is 5.4. But we are doing the evaluation every cycle. And we also extended our results based on estimation. And these are the numbers we just measured, I showed, and this is the real number we got. And if we are doing the long-range force computation every 4 cycles, as NAMD did, and we do the long-range part by reconfiguration with the with one of the FPGA. So the time per step reduced from 0.57 to 0.37. And if some application allow low precision as 24 bits here, and the time per step reduced to 0.22 seconds. And we have 2 FPGAs, and if user just have one FPGA, and let's assume they have the top chip of the Vertex 2 family, which is Vertex 2 VP100, and every cycle do the long range force, so it needed 0.36 seconds, and the 24 bits version is 0.31 seconds. So why we just got something like less than 10, and we usually think FPGA can do something like 100, such as on the rigid molecule docking application I showed once in this talk. Why? So the first reason we thought is we are using a 3-year-old chip, so if it just runs at 75 megahertz, but it can run as fast as 13300 megahertz, I have to admit. And by using Vertex 4 or Vertex 5 chip, it can run as fast as 500, so we can get speed up by that, a big fact. But for some marketing decision reason, the new chip did not help us in the number of the chip resources. So we limited by the resources, but they didn't help me in this direction. The second reason I think is most important because we are doing 35-bit computation, and in some applications can achieve 100, such as protein docking. We are just doing 2 bits by 2 bits or 4 bits by 4 bits computation, but now we are doing 35-bit computation. So that's limited the number of processing elements to do the convolution. And that's the biggest part. And if we have the hardwired floating point module of FPGA sometime later, we can improve the speed up by this one. And the third one, we just got everything implemented on FPGA, and as I said, it might be the first publication. So we didn't do much optimization. And our test bench, like NAMD, it has been optimized for 10 years, of course in different ways, but that might be one thing we can explore. So since we just get sometimes some speed up like 5 or 10, is this good enough? Well, we believe it still worth to do that even at this moment, because reduce something from 100 to 20 times, it's still important. And I talked with some chemists, and they are complaining they have to just kick off one simulation and run a couple months to get the data, and if something wrong, they have to do it again. Well, that's horrible. So they want even a small speed up. Another one is we are running at a slow frequency, so it saves the power. As I say, the power density problem maybe not that critical here. And of course, molecular dynamics is so important by that many applications. Okay, so MD people care about. And a summary about the multigrid we did. We want to do that, and I'd like to talk about this now because I think the problem can be mapped to FPGA very well because of the particle grid conversion, the tree structure, the convolver, the 3D spherical array. And the speed up we got here, I think it's still good. And we got accurate result even without double precision computation. And the multigrid is complex, and it can solve, I think it can solve any PDEs, but we need to investigate the problem specifically. And there are many applications can using this structure to the multigrid. So there are lots of work to do. And this is a short conclusion about accelerating high-performance computing with FPGA. So first, the potential speed-up is very promising. That's true. But we need a very careful design. We need to select the problem very carefully. We just design the algorithm, such as we do on multigrid instead of FT. And we need very careful logic design, like the tree structure, the arithmetic mode, and this stuff. And then we can achieve speed up. And this effort is so big, so which means it's not that easily can be done, even by an expert to spend months on that. So we also need development tool to help us, either in developing the logic and or to mapping the whole problem. So that's the end of this talk. And I promise to show you some slides about the semi-floating part. So let's do it quick.
I have a question on the performance and how it's affected by the latency, meaning the fact that you have to move data from main memory to the board and back. Is that how does it affect the performance of this particular application?
Okay, let's see, and let's find the figure so I can point to it.
Exactly.
So we're downloading the data. So that's a good question, because how that traces back to how we partition the problem. So why we just do part of the problem, and why we did not just implement the pipeline to do the computation? Because we are thinking if we want to download the data, such as just pairwise, send a two-particle data and do the computation and send it back, the communication itself comes to O(n) squared. And we don't want to do that, so we ship all the particle positions onto the board and do the computation self-contained on the board. And so the downloading stuff the communication comparing with the computation is very small, as you see here. The communication and the overhead is just 25.6 of 500, and most of the time I was spending on the first two parts. So in this problem, communication we don't have to optimize too much.
So one question is how does this compare to some of the other acceleration techniques, let's say clusters, something like SETI at home, or even DSPs?
Okay,
why is the FPGA good here?
Okay, if we want to do the computation with clustering, so multiple processor problem, but that's kind of different from this one. Okay, thank you. So that's kind of because we are accelerating. We can say we are just accelerating on the node performance instead of the whole system. Of course, we give the whole solution, So we can do the other computation. But since this is only one board plugged into one computer node, this is the model we are presenting here. But if in a cluster, we can have multiple boards into multiple nodes to the computation. And that's why we have different core processors. And these core processors can be implemented on different nodes if they have FPGA board. So that is the comparing with the cluster. So it's not a direct comparison.
Right.
And to do something else, and I think one thing we can do might be like a GPU or DSP, and they can do good stuff about the convolution, I think. Right, for example. So that's the basic case they can do, of course. But they cannot do the particle grid conversion that quick. And in the best case I will think is I'm using the FPGA to do the particle grid conversion, and there is a very fast array to do the convolution with GPU plug after that. But such kind of problem will be so specific, and the FPGA is more general than that. So if we swap to another big chip, so we just replicate the number of pipelines for the short range force and increase the number of processing elements in the multi-grid. So we can easily, it's more flexible on FPGA.
So this doesn't really reconfigure the processor. So if you would actually do a custom chip that would work, but
yes,
you couldn't justify the cost, which would be a couple of million or something to design it. Or,
that's cheap.
Yeah, that's what I'm thinking. Like it seems cheap. So why don't you do that?
Because FPGA is a commodity part, so you can buy these chips because they are on the shelf. But if you want to design ASIC, well, it takes a long time. And how about if there are new algorithms come out?
Right.
So, and I think there is a Japanese group. They are doing ASIC to do an n particle problem with ASIC. And so their progress is kind of slower than the FPGA evolution. And another reason is, again, ASIC is kind of specific. If we just want to build a machine for market dynamics, that may be possible if people just want to pay the money to buy speedup. But as I said, if we are building supercomputers like SGI, Cray, even Microsoft, we all want to build a machine to give a general solution, not a point solution. In that case, FPGA, of course, is more flexible. And it gives either more market opportunity and research opportunity. And if we want to spend time waiting on ASIC, why not we spend time on developing, since it's more general, it can attract more interest, more research effort on that. So.
I guess the other kind of corollary is that is there some opportunity for where you could actually do dynamic reconfiguration that would be somehow useful here, right?
Well, that's definitely another axis in the design space.
Right.
So in this case, because at this moment the reconfiguration is kind of expensive, and the chip is not that big enough, so we have to spend all our resources on one specific task, and even that we think it's not enough. And so in some specific case, and I show later, we estimated on the timing, we do the reconfiguration for the short range, for the long range for every 4 cycle. We can have some data, we can have some speed up. So that's possible. But because this is just the first step, so we didn't go that deep into the reconfiguration part. And partial reconfiguration is even beyond the scope.
Different question, but same question, different way. Is there anything here that is dependent on the data?
Dependent?
Describe the algorithm and how you partition and whatnot. And since you're using this semi-FP, you do have to do numerical analysis of what kind of input you're going to get.
Exactly. And I'm using the 35 bits and the semi-floating points. And I think I'd better to show the semi-floating point slides a little bit. And the reason for the reason of 35 bits is there are 18 bits multiplier on the FPGA, and the 1 bit is for the sign, so pair of them is 35 bits. And we need to do numerical analysis based on the problem to decide how to implement the semi floating point. As we can see here. We don't want to do floating point because they cost too much area. And we just semi-floating, so it's much smaller. And the floating point has, well, it's too expensive, but it covers a big range of the range of the data, and it's quite flexible, and almost we don't have to think about overflow. And the fixed point problem is it's cheap, but the dynamic range of the data is huge. And we do interpolation for the short range force. And we can see the coefficient at this area and the coefficient at this area, they need more than 100 bits to cover the dynamic range. So it's impossible to do fixed point number to do the thing from this end to this end. So we use semi-floating. And we can see here, we do the interpolation piece by piece. And between interval by section by section, the term here. And in each section, the format of the bits are different. So we have the same input bit string, but we interpret them in different ways. And how to interpret them, so where is the decimal point is predefined based on the curve. We analyze the curve in advance and find out where is the point is, and where, for example, in this area, what is the biggest number and where we should put the decimal point. And this is the idea of this one. So we have a string, and we do not have any format information combined with this bit string. But once we send it into the computation module, we can find out which location, which section it is by finding the most significant one. So that's the section, and we call it format. And this number must be generated format here. And we will carry this with the computation through the pipeline. And then we also get the offset for the computation, for the interpolation. And during this computation, there are two operations, addition and multiplication. We have the same bits without bits, but they have different formats. So we need to align them in different ways based on the format of the section, or in other words, where is the decimal point. And this is the multiplication. The multiplication is easy, just multiply and do the switch to align the data. But this one, we need to align the data so they can add them together. But the difference between, so for double precision, floating point is doing the same thing. They align the data. But since we predefine the formats, so there are just a small number of them, and we predefine them, so the switch logic here is much, much smaller than what you need for the floating point number. And of course, this solution is very close related to the problem itself. So that's why we need numerical results to validate our implementation. So did that answer your questions?
We'll talk later offline.
Okay.
Another question.
Okay.
You say you can save power by using FPGAs. And I see two great big fans on top of your two FPGAs. Look, are you saving any power per computation?
Well, I should be modest to say that, because my advisor bought this board.
Your advisor what?
He bought the board. We didn't design the board.
I understand. Yeah.
So how much power we can save? We just claim that because we did not because we have the data, but because we are thinking they are running at a slow frequency. And based on that, we claim, well, they might have less critical power density problem.
You can read the thermal specs, or touch your finger and jump up when you burn it.
I dare not touch my finger with microprocessor, so I cannot do the comparison first. Of course, you are right. These chips, definitely, they are very hot. And, but no, I'm not an expert about on the VRS side of the power analysis. So,
next.
Yeah.
But usually, like FPGAs take like 5 times more power than a fixed logic for the same. So then you are claiming that your calculation is more than 5 times faster using this than if the same transistors using fixed logic. I think that's the essence.
Yeah, because you know what? The day before yesterday, I talked with my friend, and he's doing on VRS side those electrical engineering. And I asked the question is there any test bench we can evaluate on the relationship between the transistor, the number of transistors, and the function? Which means if we want to implement a floating point multiplication, and how many transistors we have to use. And based on different technology, if we're doing ASIC, we need just a small piece of area. But for FPGA, we need a big area because we save the freedom for configuration. And also, if we are doing on the microprocessor, well, we waste a lot of things because most of the time just part of the chip is working and the rest of it is just running, taking the power. And is there any measurement to do that? And once we got some data or some measurement like that, we can easily give a over picture, say, okay, now we have a problem based on the power. Which technology we should use? Either microprocessor, or FPGA, or ASIC, or something else. And okay, so that's what I thought about, but it's definitely not an answer to this question. So,
did you do anything specific in your implementation for power management? Like, for instance,
no.
There was a paper at FCCM last year, I think, that it got a 70% power reduction simply by rerouting the clock, avoiding spreading clock all over the place.
Actually, I haven't read that paper because I'm not caring about the power at this moment. Because the board is just plugging my computer and it runs well. But I think because slow down the frequency is one part of, so we can save the power. And there's some other trick. I think it's related to the implementation. I mean the VRSI implementation of FPGA. As I know, one trick at Xilinx is they always use negative clock cycle. I mean clock edge. So they didn't use if something equals 1, you do something. If something equals 0, and I ask why, and say, well, this turns out to save energy. But the people told me that he didn't know the reason. But that's most of the logic they design, so use something like that. So there are a lot of technology, I mean, related to the FPGA chip implementation itself. And I think based on my scope, I can expand the parallelism, slow down the frequency. So that's the best thing I can do about FPGA saving power. But beyond that, it's related to the chip implementation. So I think that needs different experts. Okay. All right. So.
Any more questions?
Okay. Thank you. Thank you for being here, and thank you for keep watching.